All right, I guess as people are coming in, welcome everybody. Hope you got a chance to get out, see a little Boulder. People online, maybe that might have been a little harder. But hope everybody had a nice evening. Welcome to day 2 of the workshop. Today we're going to focus more on the atmosphere and land, multi-year predictability, and towards the end of the day, start getting into applications, which we will continue tomorrow. And we'll also talk a little bit about different prediction methods, numerical prediction on the one hand, and empirical machine learning on the other. Just a couple of reminders for everybody. The presentations, the slides are linked on the agenda. So if you go on the agenda online, there should be a button as they pop on. So feel free to look at them if you want to be reminded of anything or if there's something you're trying to remember. Also, I don't think I mentioned it yesterday, but we've kind of taken the approach of having people add additional methods slides, kind of describing maybe a little more detail of the methods they may have used at the end of the presentations, which were not presented at the time. So again, if you're interested or have other questions, feel free to look at those. Remember, you can ask questions both in the chat on the WebEx and in Slack. Slack right now, it's mainly crickets, I think. So feel free to use that. Maybe we'll put in a clue to the $1 million prize in one of the channels in Slack. So you may have to go through that way. And the last thing is for the people who are speaking both online and in person, remember that you don't have control of a pointer. In here, you have a laser pointer, but the people online obviously can't see that. So just make sure if you're pointing to things in particular that you're clear about where on the slide you're pointing. And with that, I think we'll get started a little early. So I'll give it over to Ben.
Thanks, Matt. I want to introduce Toby Alt, who's also the co-chairing or moderating the session. Toby's going to be taking notes, so if you have anything you want to make sure it gets in the notes, let Toby know. Our first speaker is an invited talk, Understanding Multi-Year Land Surface Predictability, from Andy Wood from the National Center for Atmospheric Research. So Andy, take it away.
Okay, well, thanks. Good morning, everyone, and thanks for the invitation. It's great joy to speak about this. I'm going to talk about understanding multi-year land surface predictability, hydrologic predictability. It's not going to be a land atmosphere talk. It's going to be more of a watershed hydrology talk. And I should say that for the last 20 years, I've been focusing more on subseasonal to seasonal predictability, but there's starting to be a little bit of work on the decadal side or in the multi-year side. So I'm going to try to touch on that. Let's see. Okay, so it will come as no shock that land predictability is different than climate predictability. So I'm going to spend just a few slides talking about the general concepts. Basically, I think we have it a little bit easier than the climate prediction task because our land predictability comes from two predominant sources. If you think about a watershed and where the moisture is stored and how the fluxes of moisture and energy go through the watershed, there are two main types of sources you can think about, and they align nicely with the initial value boundary condition type framework of earlier work to do with atmospheric predictability. So we have hydrologic predictability in the watershed, basically everything that's stored at a certain time and will move through the watershed and out of it. And then we have meteorological predictability, which is basically the future climate forcings that will impact the watershed. So kind of the boundary conditions or boundary values. And so that's important. Another thing to mention kind of in passing is that the land, unlike the atmosphere or certain atmospheres, certain aspects of the atmosphere, is a damp system. So there are a lot of negative feedbacks and restorative forces, which provide a certain stability that, according to some people, can add to the predictability of the system. You know, if we think about large anomalies in moisture, like when the states of the watershed are very wet, they tend to drain out faster, evaporate faster, sublimate faster, and so it's pushing the system back toward normal. And conversely, on the dry end of things, when the watershed is dry, it tends to drain out slower, evaporate slower, and so it's sort of, again, pushing it back toward a normal. So that gives it a sort of damped stability, which is nice. And then lastly, we can, and this is a part of the good news, we can benefit from a kind of predictable evolution due to the annual cycle, driven mostly by temperature and radiation changes in that seasonally. But in some parts of the world, you have a very nice sort of evolution of things that happen to the land surface that can add up to a year of predictability. So for instance, I'll just walk through it. Thinking about a snowy basin in the west, called Crystal River up in Colorado. I've sort of mapped out some modeled components of the water balance. So soil moisture, precipitation, which is in gray in the plot on the left, and snow or equivalent, or SWE, in green, soil moisture in red, and runoff in blue. And if you can do a reasonable job at predicting winter climate, say you're in June and you have some ability to predict climate the following winter, so that's a 6 to 8 month lead time, and that is going to determine the spring snowpack, which will build up predominantly during the winter and then reside there for a number of months and eventually melt and lead to early summer runoff. And then that runoff and the impact of the snow and the soil moisture will provide a signal that lasts all the way out to the following fall. So right there, you've kind of boosted your initial climate predictability into a much longer lead land predictability. So that's another nice feature of the watershed. So for the most part, over the last 40 years, or even longer, going back to the early parts of the last decade, the attempt to predict land surface hydrology has relied mostly on initial condition predictability. Basically, all the methods try to capture or measure or estimate the moisture in the watershed, whether through models or through observations of snow, and then use those to initialize a forecast. And so it's a combination of kind of an assumption of a perfect initial condition with a climatological outcome. And so you end up, most of the signal in our predictions comes from that initial condition. It's often fairly linear. The uncertainty tends to come from this meteorological uncertainty. So we can use hindcasts made in this fashion of this perfect initial condition to try to understand predictability if we look at them over a long series of periods. So on the right, we have a depiction of a prediction of a seasonal spring runoff volume that's made every year from October through May, I guess, or through June. And you can see how the spread of the ensemble is shown with the dots, and you can see how it kind of shrinks as you go through the season. Quite some time ago, I started to get interested in this change of uncertainty as you go through the prediction cycle. It has to do with the seasonal cycle. And so I came up with this way back in like the early 2000s of kind of reshuffling these hindcasts so that you could, instead of look at these initial condition driven ensembles, you could look at kind of, or meteorological forecast ensembles, you could look at initial condition ensembles. And I called this technique reverse ESP. So down on the bottom right, where you make an ensemble by compositing all the initial conditions across history and combine it with the perfect climate forecast. And so this became a really useful structure comparing the error in these two different types of forecasts, like as a ratio or in some other formulation, to see which component of predictability or uncertainty is dominating the forecast as you go forward. And so this is just an example of looking at a location in California on the top right, Shasta Dam, where if you start out making a forecast in October, climate forecasts dominate the uncertainty, or climate uncertainty dominates the forecast uncertainty. So climate forecasts are more important than initial conditions. And conversely, if you're down in the Rio Grande in the Southwest, starting in October, the initial condition is more important than the climate forecast. And you can even push this further. I sort of cycled back to it about 5 years ago and did a whole lot of experiments where I blended perfect and climatological information across at different levels in the initial conditions and the boundary forcings to show that depending where you are, these contributions vary really strikingly, seasonally and by location. And so this is an example of like showing contour plots of 3-month runoff prediction skill as a function of initial condition uncertainty and boundary climate forecast uncertainty. And as you can see, like if you're initializing a forecast in December for the next 3 months, the runoff prediction variability and skill is almost entirely determined by the initial condition uncertainty. And if you're looking at it a bit later, initializing in February, going into the spring snowmelt period, the runoff forecast is almost entirely determined by the boundary forcings, the climate that's going to hit the basin and determine how fast whatever snow is there is going to melt. So it's quite dramatic. If you look down in the southeast, a more humid basin where you don't have such strong seasonal cycles, you see that runoff predictability in a 3-month period is always a blend of initial condition and climate boundary forcing predictability. So we use this type of analysis really all over the country. It caught on over in Europe, so there have been a lot of analyses of like European basins and global basins for how their predictability works with regard to these two sources. And we've even looked at it in a decadal sense. So going further to define a concept of a forecast skill elasticity, which is kind of the change in your ability to predict something depending on the change in the accuracy of an initial condition or a boundary forcing. And so this is a paper looking at total water storage in basins around the world and how the decadal climate forecast predictability compares to the initial condition predictability. And interestingly, if we look at the top right, we see that in a basin like the Amazon, which is humid, this prediction skill for lead times of 1 to 4 years is strongly dependent on climate. It makes sense. It's sort of constantly cycling moisture through these basins. If you go to like the Yenisei, which is a more northerly and more arid basin, you see that there's an initial value predictability that goes out for 4 years. So these kinds of analyses can teach us a lot about how our land surface, we expect it to respond. And so given that sort of background on predictability, we'll look at how actual sort of experiments on prediction are panning out. So there have been a number of decadal prediction experiments that others have talked about. There's this new SMILE project being led by people like Steve Yeager at NCAR, which are examining how much skill you can get out of actual ensemble model forecasts. This shows that, for instance, looking at lead months 7 to 11 and 12 to 16, there is notable temperature prediction skill, even in the continental land areas, and as well as a bit of rainfall prediction skill. Not as much, but just a hint of it in North America. And if we go further in these experiments to look at how the skill going out into the second year pans out for hydrologic quantities like total water storage, we can see that, for instance, in the Southwest, we have what looks like some significant skill going out even to like month 19, which is halfway through the second year. And you can see from the top right plot that there's, definitely these decadal initialized predictions have a stronger agreement with observations than uninitialized predictions. So that's very promising. And then we can, well, it's promising on one hand. Some skill exists in some places. On the other hand, if we look at most of North America, particularly most of the US, there is very little significant skill in this kind of quantity, but we can at least try to understand why we're getting it in the Southwest. And one way to think about that, or I've started to think about it, is in terms of the ability of the land surface to cycle through the moisture supply at a regular time interval. So if we compare a basin, say up in the South Forth Flathead, in Montana, the inflow to a Hungry Horse Reservoir, if anybody pays attention to reservoirs. We can see that in that system, this is a plot of total soil water in a model. The soil water is able to reset itself pretty regularly, almost every year, maybe not every year, but pretty frequently. Whereas if you look down in the Southwest, such as in New Mexico, Rio Puerco, we see that, if we can infer the soil moisture storage capacity from the ranges of those lines, and we can say that there are significant multi-year periods in which the rainfall is not able to reset the soil moisture, and so that leads to land memory. And so with these kind of concepts, I should also say we do a lot of work with stakeholders. So in one particular project, we're looking at multi-year prediction in the Colorado Basin, so particularly predicting the second year of inflows to the reservoir system. This is with reclamation, a bit of funding from NOAA. And here we're using hindcast again to go back and look at how well initialized predictions can have any skill at a 2-year lead time. And so in the bottom plot, we're looking at 24 lead months going up to the end of the second year. And after the first year, you start to blend in the observed flows. So the skill or the error of the forecast drops quite a bit. But we see that there's some evidence that we do have this multi-year prediction where the initialized predictions in blue and yellow, even starting 2 years out, are starting to have a little bit of lower error than the uninitialized climatological predictions. So this idea of there being predictability is evident not only in scientific but also applied studies. And so I think we're at a point where we can sort of work toward a misspelled understanding of terrestrial decadal predictability. I think some indicators of what controls predictability on the land surface and in climate can be combined in ways that can give us expectations of where we should find predictability and where we shouldn't find it. Like one sort of, summary view of some of how you could combine some of this knowledge is in this little graphic where if you think about land surface, the land storage divided by the annual precipitation being an indicator of where you have a lot of potential memory, we can see that there are going to be places where we have that. And if that's combined with climate predictability, such as in the upper right, we may have predictable multi-year prediction that's driven by both initial conditions and climate forecasts. So we have these excursions from normal driven by climate, but they're maintained by this land surface. And then in other parts of that sort of graphic, we don't have all those components together and we have lesser predictability. So I won't go through all the boxes, but I'll go to my final slide, which is just that I think in thinking about this as scientists and doing applications, it's really important to keep in mind this kind of organized concept of where predictability is and where we can exploit it and what's contributing to it. I think being able to develop expectations of predictability is very helpful because we do an experiment, our eyes are drawn to the place where we get the positive result. We'll show, oh, you have predictability here in the Southwest, and we look at that. But we tend to miss those places where we should have a positive result, but we don't get it. And that's a place where we want to dig into our results and say, okay, why is this not working? If we don't have any expectations, we don't have any way to sort of apply that thinking. So anyway, S2S to decadal hydrologic predictability varies time, space, season. Climate system mode is conditional hydroclimate. I'd say we're in a place where we can have forecasts of opportunity. We won't get them everywhere and always, but where we have skillful climate forecasts and where the land hydroclimate is conducive, we should have some ability to do multi-year prediction. And I would also say this knowledge is still developing, as we'll see in this particular, this workshop and many others. There's a lot of focus on the climate aspects of it. So we will focus on our ability to do multi-year prediction of ENSO, but there's a degradation of that signal as you get toward the things stakeholders and others care about, such as continental climate and runoff and things like that. So we just need to be clear when we're talking about where we are, how far we've gone toward the kinds of things that a stakeholder would care about. We're pretty comfortable with the idea that, you know, we can exploit trends in temperature, as I think Aaron Tyler's poster talks about, if you get a chance to see that. And the stakeholders are comfortable with that. They see it happening. So that's one aspect we can currently hinge a little bit of predictable conversations and applications on. So anyway, those are my thoughts from the morning. Thanks for paying attention this early.
Thank you, Andy. Really appreciate that. We're going to move on to our next speaker, who's online. Adam Scaife is going to. We'll take questions in the discussion session. But Adam Scaife is online. He's from the UK Met Office and also Exeter University. And Adam is going to talk about representation and predictability of the QBO in global models and impacts of the QBO on tropospheric predictability. So, Adam, please take it away.
Thank you, Ben. Can I just check that you can see my screen?
We can, and we can see your laser pointer too.
Brilliant. Okay, thanks very much. So thanks for the invitation to speak and also for the topic. The quasi-biennial oscillation is a very good fit for this workshop, I think, because its inherent time scale is obviously multi-year. And so what I'm going to do is to give you an overview, really, of the current state of the science for the QBO in terms of its representation in climate models, its predictability on the timescales considered in this workshop, and then we'll have a look at its teleconnections to the surface climate. So I'll start with these three pictures, which give you an overview of what is the QBO, for those that are not so au fait with it. The picture on the left is a long Hofmuller plot starting in the 1950s when we first started to observe and measure the QBO right up to the current time. And this is plotted as a function of height and time over the equator in the tropical stratosphere. So this is the QBO itself. As you can see, it's an oscillation, roughly 2-year time scale, average period is about 28 months, between westerlies in grey and easterlies in white. And there are, as well as the very striking, there's no filtering, by the way, in this picture. This is actually what the winds look like in the zonal average on the equator. And you'll see, as well as the very striking oscillation, there are lots of other interesting features. For example, the asymmetry in the amplitude. So the westerlies tend to be a little bit weaker in amplitude than the easterlies. And occasionally you get these stalling of the descent of the easterlies, whereas the westerlies tend to come charging down much faster. So there's a few asymmetries and subtleties in there, and I'll explain in a moment how well they're modeled. But let's look quickly at the surface teleconnection. This is an example shown here in the middle in terms of sea level pressure. Now this is generated by simply looking at the sea level pressure in winter, which is when the teleconnection is strongest, by the way, between the easterly and westerly phases. So just take a simple composite of all the years, all the winters when it's in easterly, and subtract away the westerlies. And then out pops this Arctic oscillation-like pattern, particularly strong in the North Atlantic basin, projecting strongly onto the NAO, or the North Atlantic Oscillation, with high pressure over the Arctic and low pressure over the subtropics and mid-latitude, corresponding to a weak jet when the QBO is easterly. So that's interesting, and the amplitude is a few hectopascals, so it could be of interest for multi-annual predictions, as we'll come to in a moment. In terms of the strength of this, although it's a few hectopascals, it only makes up a small component of the total variance in this pattern. An example here is shown from this paper from a few years ago now, showing that there is, however, a small detectable peak in the power spectrum at the period of the QBO. So in terms of how well this is reproduced in the models at the moment, I've picked these three examples, one from very early in the development of models of the QBO. This is from Takahashi et al. About 20 years ago, which I think really, if my understanding is correct, represents the first decent simulation of the QBO in a 3D climate model. And the way they achieved this oscillation in their model Previously, by the way, models, often just had a blank picture, a blank screen. If you plotted this picture, you'd just get weak easterlies throughout, no oscillation at all. And the breakthrough that Takahashi made was to reduce the amount of diffusion in the troposphere in their model, and that allowed the convection to generate more gravity waves, which propagate up, break, and generate this oscillation. I haven't got time to go into the mechanism, but it's pretty well understood. So they did that by reducing the diffusion, but that did have some side effects, and they had some rather spiky precipitation fields in the troposphere. So there was some damage to the tropospheric climatology. The method we used a year or two later, which I think is kind of carried through and is now used in many of the models shown here on the right, is to really simulate those gravity waves, or rather parameterize them using fairly coarse resolution models, but adding a parameterization of the gravity wave spectra. So this is gravity waves, not like the ones you get off mountains with 0 phase speed, but in this case with multiple phase speeds, which are important for the oscillation. And when we added that parameterization, after a bit of tuning, we were able to get an oscillation that looks pretty realistic in terms of both the asymmetry and the strength and the period of the oscillation. And since that time, I think the current state of the art is pretty well represented in this recent paper from Jadwiga Richter, showing that basically a large number now of models do have some kind of QBO representation. So that's where we are. Maybe half the models or so have a decent representation of the QBO. In terms of what drives that in the models, I'll just quickly reiterate that it is the parameterized gravity waves.
Adam? I'm sorry,
yeah.
Adam. Yeah, so I hate to interrupt you, but the slides are coming across somewhat oddly. And I was wondering if it's okay if we drive the slides.
Okay, it might be because I'm using, if you're on a Mac, I guess. Is that possible?
Yeah, I'm not sure quite what it is, but
okay. Hang on.
But yeah, some of the slides become unreadable, and we don't want that, obviously.
I see. Right.
So, sorry about that. I think, are we on that one, or?
Yeah. Did you catch the last stuff, Matt?
Why don't you want to go back one slide? Yeah, maybe.
I'll give a 2-second recap of this one.
Yeah, I think, yeah. Okay, so we'll go forward.
Okay. So this is just a bit of history about simulation of the QBO. Picture on the left is one of the very early simulations that was successful because it reduced the amount of diffusion in the model, allowed gravity waves to propagate up and generate the oscillation. In the middle panel, our approach was to use a parameterization of the non-orographic gravity waves, the waves with finite phase speed. And that method is used today in about half of the climate models, which is shown on the right there, to generate a reasonable QBO-like oscillation. Next slide. Just very quickly, just to recap on the mechanism here and what drives the QBO. The black line in this time series shows you du dt, the acceleration of the wind in the QBO region. The red line shows you the parameterized gravity wave forcing. So this is the momentum flux driving the wind oscillation. And then the yellow line shows you the advection of wind that's contributing to that momentum budget. And the blue line shows the explicit wave driving of the oscillation. And just very briefly, what's dominating the modeled oscillation is the X term, the gravity wave forcing from our parameterizations, with some contribution from the others. And of course, the yellow term, which corresponds to upwelling in the tropical stratosphere, is opposing the wave driving. Next slide. So that gives you a very brief summary of where we are in terms of modeling. I would say at least half the models now have a QBO, and of course some of those are being used for multi-year prediction. So what does the predictability look like? What do we know about that so far? This picture shows you examples from two systems, one from the Met Office and one from the Max Planck Institute in Germany. And these are just particular forecasts starting in November 1965 and run out for a few years into the future. You'll see that the model in blue, and that's an ensemble mean, follows actually quite closely the analysis of the winds in the QBO region in the lower stratosphere very well, even out to a few years ahead, showing straight away in this simple example that there is a very high level of predictability, multi-year predictability for the QBO. Next slide. If we look at that over a whole set of hindcasts, for example, from the 1960s up until the present day, as we typically do, then we can start to characterize how the predictability varies with lead time, and that's what's shown in these diagrams. The picture on the left shows you the correlation score for the QBO winds as a function of lead time. And you'll see, if you look at the red line, which is their model with a good QBO, in this example, that the correlation is very high for the first year, but present actually even out to a few years ahead. If you look at the middle panels, the ones from the Scaife et al. Paper, you'll see that for these two models now, this is the Met Office and the German model again, that the correlation skill as a function of lead time decays quite slowly as we progress through the forecast lead times. In fact, these scores are higher than the predictability of ENSO, even though the QBO is a purely atmospheric phenomenon. So it's very important that we remember, I think, that not all long-range predictability stems from the ocean. Having said that, in this case, because of the great regularity of the QBO, it turns out that you can actually match the model skill simply using a cosine function of 28 months, which of course isn't very impressive, but nonetheless, this mechanism in the atmosphere is predictable out to at least a couple of years, if not 3 years ahead. And then on the right, we have a more recent paper showing similar results now from a whole bunch of models, which are able to predict the QBO. In this case, it's just out to the 1 year lead time. Next slide. As we go along, I want to point out one or two outstanding issues. And the first I want to highlight is this problem with the amplitude of our predictions. These pictures show a profile of winds from 70 hectopascals up to 10 hectopascals on the vertical axis. And the wind strength is on the x-axis for both easterly on the left and westerly on the right of the vertical line, phases of the QBO. And there's a whole bunch of models in here, and they all show the same problem. And that is that as the lead time progresses from T+1 month in the top left to T+9 months in the bottom right, you can see that the amplitude in the models is decreasing below that in the observations. And this is generally seen both in free-running models and these forecasts, that the amplitude in the lower stratosphere is underrepresented. So that is a systematic error that is common to models and ought to be a focus for future research. Next slide. Another important thing that's arisen recently, and is slightly ironic given that in 2014 we published this paper based on hindcasts up until roughly that time, showing the really high level of predictability of the QBO, is that just a couple of years later, for the first time in our observational record, there was a disruption to the QBO, completely unexpected. The circle is circled with that black circle there in 2016. You'll see that all of a sudden, after 60 years or whatever of very regular behavior, all of a sudden the westerly phase collapsed in late 2015-16 and gave rise to a transient easterly phase. And that actually happened again in 2019. So there's been a couple of recent disruptions to the QBO. And as I say, these were not predictable. So perhaps the predictability of the QBO is not quite as high as we might have thought before, although having said that, in the periods in between, of course, it behaved very similarly to the forecast and to previous periods. Next slide. This is just to illustrate that it wasn't predictable on even seasonal timescales. The top panel here shows you a height time off-Muller plot of the QBO winds in the stratosphere over the equator. The upper panel shows very regular behavior, as you would expect, and in the forecast. And then in the bottom, you've got observations which show around early 2016. So if you look at sort of 2016-04, April 2016, you'll see that there's an easterly phase impinging, which was not forecast. Next slide. So let's turn now to the teleconnection. We've looked at the modeling of the QBO. We've looked at the predictability of the QBO. Now on to in the last section, look at the important question of its impact on surface climate. And I wanted to start with this picture on the left, which is produced by a guy called Bob Ebden, who used to work at the Met Office, actually, who was one of the discoverers of the QBO. And a few years after the discovery, he published this paper in 1975, which I think has largely been forgotten about, but shows this teleconnection to the QBO. So if you take the easterly phase of the QBO and subtract away neutral years, you see a picture here in the, sorry, that should be 1,000 hectopascal height, not 100, I apologize for that. In the surface circulation, showing a kind of dipole over the North Atlantic. And that, of course, is very reminiscent to what I showed you near the beginning for the current teleconnection and is repeated in that third picture along. So even back then, there were signs of a surface teleconnection. The Thompson et al. Study in the second picture shows the impact on surface temperature. And you will see a kind of quadrupole pattern there for easterly QBO, with cold over Northern Europe, mild over the Mediterranean, cold over Eastern US, and mild over Eastern Canada and Greenland. And that pattern has held up. It stood the test of time, because if you look at the pictures on the right from my paper or Anstey and Shepard's paper, you'll see there very similar teleconnections that match what was found in the early papers on the teleconnection. And the right-hand panels show you that there's actually a weakening of the polar night jet throughout the whole depth of the atmosphere during easterly QBO. Next slide. Having said that, although there's a good teleconnection in the observations which stood the test of time, the models are more flaky. And this picture here shows the observed teleconnection on the top left, and then examples from 4 models, and this is just on seasonal timescales, showing that actually only some models get the teleconnection, and overall it is rather weak and different amongst different models. So there is still a problem with simulating and predicting the surface teleconnection to the QBO in our climate models and indeed our multi-year prediction systems. Next slide. That's just reiterated here, really. If we focus on that middle panel, this paper by Bohr and Hamilton actually estimated using observations how much of the unpredicted surface climate scale, I think this is in 500 millibar geopotential height, so tropospheric geopotential height, how much of the unpredicted variance could be attributed to the QBO. And suffice to say, there are some patches in there where the variance that would in principle be predicted, could we do a perfect prediction of the QBO and its teleconnection, are large in some regions, so it might be worthwhile to pursue that. However, if you look at the picture on the right, from a very recent paper, you'll see PDFs from model simulations, which are those tall, narrow PDFs from very large samples and model simulations. They're clustered around 0, slightly positive. This is a regression of the NAO in this particular climate forecast system against the QBO. So it's showing you get a very small change in the NAO per QBO standard deviation, whereas in the observations, although it's rather uncertain and has a very broad peak, it's several times higher, hinting again that the surface teleconnections are very weak in our prediction systems. Next slide.
Adam, 2 minutes?
Yeah. Okay, yeah. So a couple of questions now and a couple of points about teleconnections that go beyond the so-called Holt-Tan pattern, another early paper that uncovered that surface teleconnection to the QBO. If you look at the Collymore et al. Results, that panel A on the left at the top, you'll see that during QBO easterly, the dashed line is below 0, suggesting that the OLR in the tropics is actually reduced and that convection is increased. And that's backed up by the middle picture at the top by Lees and Geller, showing an increase in rainfall during QBO east. And other studies have even gone further and argued that there are tropospheric wave trains, for example, in that Garfinkel and Hartman paper, but also the Yamazaki paper, which propagate right across into the extratropics, away from the tropical rainfall region, as might be expected. So there are some other suggestions of wider teleconnections to the QBO. Next slide. And I'm going to show this at the end. This is the last one I will show. This is looking at this very recent finding that the QBO may even affect the activity of the MJO. So we know the MJO is very important on subseasonal timescales, but there seems to be a signal where if you look at panel A, in winter at least, the QBO is correlated with the activity of the MJO, the amount of variance in the MJO, such that an easterly QBO drives an increase in the MJO activity. However, if you look at panel B, that's only really true for the recent period. That's the strength of this teleconnection over time, and you can see it's very strong at the end, near 2000, but decays away if we look further back. So there are some questions about it. And on the right, you'll see an estimate from our seasonal forecast system and our model, where we've tried to reproduce this, and the model is not able to reproduce the link between the MJO and the QBO, as indeed is found for other models. Last slide. So I'll stop there and I'll just make a couple of quick comments. I think it's fair to say that a growing number of models now simulate the QBO. They mainly use this method of parametrized non-orographic gravity waves. It represents, I think almost uniquely, an atmospheric source of very long-range predictability. So amazingly, we've got predictability on multi-year timescales originating in the atmosphere. And it does offer some predictability of surface climate on multi-year timescales in the regions where its teleconnections are active. I've also highlighted a few problems though, because I know this workshop wants to do that. One is, why is the oscillation too weak near the tropopause? That's not understood and is pretty much universal across the models. Another question is about the sources of gravity waves that drive the QBO. Some groups have gone quite far down parameterizing the sources of waves, but I'm not seeing yet any very convincing studies about whether that can lead to improved predictions, for example, through coupling to ENSO or something. Another really important question, perhaps the top question, is why are the teleconnections to surface climate too weak in the models? It's really that reason that is limiting the utility of the QBO for providing surface predictability, and I think there's some way to go on that, and I'm quite hopeful that we will make progress in the future. And then the last one is, we have to be cautious, but there are these other teleconnection routes through wave trains and perhaps the MJO. So there's even another avenue there that might be an interesting area for future study. And if you're interested, some of this stuff is discussed in this review paper. And I will stop there. Thank you very much.
Thank you, Adam. Given the time, I think we need to move on. Our third speaker is also an invited talk. Yoshi Chikamoto from Utah State University is going to talk about assessing multi-year predictability of the Colorado River water supply using a drift-free decadal climate prediction system. Yoshi.
Thanks, Ben. First of all, thanks for invitation to this very important workshop. I'm really excited to share our recent research with you. I know there are many challenges to organize this workshop due to the COVID, and I was really looking forward to seeing this workshop. So eventually we have it, so I really am glad to join this workshop. So I want to say my acknowledgement to organizer for their patient effort. I'm Yoshi Chikamoto, assistant professor at Utah State University, and today I want to talk about multi-year predictability of Colorado River water supply. So this research was recently published on a new Nature journal, Communications, Earth and Environment, and I want to acknowledge my colleagues, Professor Simon Wang, Robert Gios, Matt Yost, and Larissa Yukon. Okay, let's start to talk about my motivation. So Colorado River is a vital water resources in the western US, and recently we are suffering the multi-year drought event. So this is a time series of Colorado River water supply obtained from Bureau of Reclamation, which represent the natural stream flow at this Ferry, Arizona. And when we have a water shortage, that will affect a serious problem in agriculture and forestry. So lower left panel shows the probability distribution of soil moisture anomalies, annual crop yield, and fire size in the western US based on each several grid box. And then Gray line is the entire year, and the red color shows the dry year obtained from these water shortage years, around 7 years. And the lower panel indicate when we have a water shortage, which affect drier soil condition, crop failures, and increase fire size. So if we can predict water supply variability, we can also assess agricultural losses and fire risk in the future. And such information will be very useful for stakeholders and decision makers to develop a proactive management plan against upcoming drought threats. But there is one fundamental question. Can we predict this water supply variability for several years? And then, of course, my answer is yes. And then through this talk, I want to show you several proof of the multi-year predictive skills. Okay, so since multi-year water supply prediction is really challenging, so we try to simplify the problem here. So this is a schematic view to show the relationship between atmosphere, ocean, and land systems. And simply speaking, atmosphere, we can decompose atmosphere component for the 3 components: high frequency variability, less than monthly timescales, long-term trend, and lower frequency variability on interannual to decadal timescales. And then high frequency component mostly contributed from weather disturbance, and long-term trend are attributed from radiative external forcing. And then interannual to decadal, like a low frequency variability, which are mostly originate from low frequency ocean component. And all of these 3 components affect the land process. There is feedback from land to the atmosphere, but that might be the minor. And because of these 3 components, atmosphere looks like a white noise. And then if white noise forcing, so land process response to the white noise forcing might be unpredictable. But I think Andy say land process has some filtering effect, and then this high frequency component might be filtered out. And then only low frequency component can remain for the land process. One of the good example is I'm always using coffee filter. So let's think about this schematic view. So if you pour the hot water from the top, we can do that for the random, like a precipitation. But output from this drop-in coffee, this is always low frequency. And the land process also looks like this kind of coffee filtering effect, and the high frequency component can be filtered out. And then we can only see the low frequency component. So, and the low frequency component mostly originates from the ocean variability. As a result, we can expect a synchronized but time-lagged relationship between low frequency ocean component and land surface process, like a stream flow variability. And we call this is the ocean memory. But by hypothesizing that low frequency ocean component affect the stream flow variability, and then which is predictable. And then so this is our hypothesis, and I want to try to show you some result. Okay, to investigate our hypothesis, we conducted a model experiment. We use a community Earth system model, CESM, and CESM consists of a fully coupled dynamical model with atmosphere, ocean, sea ice, and land components. Those are coupled each other. And they also have radiative forcings, such as atmospheric CO2 concentrations and volcanic eruptions. And in our hypothesis, we think low frequency ocean component is important. So we assimilate observed ocean temperature and salinity anomalies into the ocean component of the CSM, and then try to run the model. So we call this the ocean data assimilation lab, and we conducted this experiment from 1958 to 2015. And based on this ocean data assimilation, we pick up initial conditions at January 1st every year, and we conducted 10-year-long hindcast experiment. And then all of these experiments, we conducted 10 ensemble members, and we mostly analyzed ensemble mean of these 10 members. There are many other details, and then some might be, you can find this paper. But using this system, we try to assess how ocean affect stream flow variability. So here we go. So this is a result. So our model doesn't have Colorado River water supply, so we need to reconstruct it based on the different variables. And the soil moisture anomalies are a good replacement. So this left panel is a correlation of observed Colorado River water supply. So that means this blue line with soil moisture anomalies based on NSF CPC reanalysis data. And we can see the higher correlation in the Mountain West. And when we take a regional average of this black box of soil moisture anomalies, which is this black dotted line, and that line follow observed water supply variability very well. Correlation is really high. So soil moisture is a good indicator for the Colorado River water supply. And then when we apply the similar analysis to our ocean data simulation, we can find also consistent result. So location is slightly different, and because of the model biases. But if we take a regional average in this highly correlated region, which is this black lines, solid line, then that one follows observed variability very well, and correlation is significant. And then when we apply low-pass filter, like 3 years running mean filter, correlation becomes much more higher. So this result suggests ocean can derive low-frequency variability of the Colorado River water supply. And then based on this method, we try to assess a predictive scale of Colorado River water supply. Here we go. So this black line is the same as before. So solid line is the ocean data simulation of the reconstructed Colorado River water supply, and dotted line is the reconstruction based on the CPC reanalysis data. And the blue line is the externally forced component, radiative forced component, and that one almost kind of flat and doesn't follow the observed variability. So in other words, this is a climate change component, and climate change is a minor driver for this Colorado River water supply variability. Right panel is a predictive scale based on the anomaly correlation coefficient. Value is higher, that means scale is higher, and x-axis is the lead time. And the black line is a persistence. So persistent forecast means initial anomaly just persists for the future. So this is just a benchmark. And as seen this time series, external host component has no significant scales. And this red color indicates our hindcast experiment started from January 1st every year. And this is a 1 year lead time. Circle is 10 ensemble means, and then error bar is ensemble spread. The point is, if you follow this red dot, which is trace black line very well. So right panel is a predictive scale. Let's see this red solid line. This is a predictive scale based on this red dot, hindcast versus CPC reanalysis reconstruction, this dotted line. And then which outperform persistent scale, and then based on this significant level skillful prediction, we can find up to 36 lead months. And then this dotted line is a scale based on our hindcast and this black line simulation. So it's like a potential predictability. So if a model getting more better, scale would be close to this dotted line. But anyway, point of this figure is Colorado River water supply is predictable for several years. And again, we only use observed ocean information, but we have no atmospheric observation, no land observation, but we can still predict it. So in other words, this predictive skill is mainly driven by ocean component. But we still don't know what ocean precursors are important for to predict Colorado River water supply. So let's see this scatter plot. This is a Colorado River water supply. X-axis is observed value, and the y-axis is the ocean data simulation run, and each dot shows each year. And the point is this lower left quadrant. So in this quadrant, observation shows a drier, and our data simulation, ocean data simulation also shows the drier. So that means this year model can predict. In other words, probably this is the ocean driving induced drought conditions. So we call this is a predictable dry years, and then if we trace back this dry year before, and we can find the ocean precursors. So this is
Yoshi,
yeah.
Sorry to interrupt. 2 more minutes.
Yeah, thanks. Yeah, I'll go quickly. So upper left is a simultaneous run, and the color shows the sea surface temperature anomalies. A contour is the geopotential height anomalies at 500 hectopascal, and there's no lag. And figure looks like pretty noisy, but if I go to 1 year before the shortage, we can see like a PNA like pattern and a La Nina like cooling. And this PNA pattern we can also see in the 2 years before and 3 years before the water shortage. And then we can find sea surface temperature warming in the North Pacific and at the 2 years before, and sea surface temperature warming in the South Tropical Atlantic 3 years before. So this ocean temperature we can use as a precursors. Okay. So this is another outcome. So I just pick up these 2 regions because we think this is a good ocean precursors, and using this sea surface temperature anomalies over this region, we develop simple regression model to predict water supply viability. So this blue line is the water supply, light color is annual water year mean, dark color is a 3-year running average, and then red color is a forecast based on regression model. And we can see year-to-year variability is not good, but the low frequency component capture very well based on our forecast. And our forecast suggests this is the 2022 this year water year, and then this is the next water years. And then our forecast suggests current drought will persist and then getting worse for a while. So it's not good news. Okay. And then you can see this forecast based on the Utah Climate Center webpage. I want to say final note about the difference between CESM-DP-LE prediction and our study. And there are a lot of differences summarized like this table, but one point might be the full field assimilation or anomaly assimilation. And then NCAR approach, they use a full field assimilation, and that one would be pretty good to assess seamless forecast, but they can introduce model drift and initialization shocks, and which may acting like a noise. And sometimes in the decadal prediction, this noise getting larger and the signal getting lower, so it will be more challenging to find a predictable signal. So we try to minimize this model drift and initialization shock, and in other words, noise getting more smaller, so we can find more easily to find the predictive signals. But anyway, there are many other factors, and at least we can have a skillful prediction. So in the future, we can enhance more predictive skills. Okay, thanks again. This is the one sentence summary based on the paper title. Coral River water supply is a predictable on multi-year timescale or in the long-term ocean memory. And if you have a question, comment, you can email to me anytime. Okay, thanks.
Great. Thank you, Yoshi. Our last speaker is in the audience. It's Sanjiv Kumar from Auburn University. He's going to talk about multi-year soil moisture predictability in the Community Earth System Model-Decadal Prediction Large Ensemble, the CESM-DP-LE experiments. So Sanjiv, go ahead.
Thank you, Ben. So there is a little change in the title. That is because of the 2 years of the work that we have done it. And second thing is, yeah, I would point out there is a poster, like some of work has been nicely described in that poster. So if you are interested in more detail, you can, yeah, I'll encourage you to go through that poster. Okay, let's, I think previous speaker had set my talk very well. I'll take it from there. Let's go to directly. Okay, so what you are seeing it here is the lake mid water level, and I pulled this data from Bureau of Reclamation, and then what I want you to draw attention is the last point that was 2021. This is annual average, and Lake Mead has reached to its lowest level, and there is a 140 feet drop. I was trying to put my head around what does that 140 feet mean. So I fitted how many of me can fit it here, and I calculated 24 of my height person can fit it in 140 feet. So this is long-term drought. This is continuing from 1998, and a more useful question here to ask is, yeah, why does this long-term drought occur? So there are two different hypotheses. One is it's remote oceanic forcing. Yesterday you have already talked about the ocean part, so I'll not discuss it more. What I wanted to draw attention in the left panel plot is you construct different indices, either PDO, IPO, or yeah, some other form of specific variability. You roughly capture the transition. Most recent transition was 1998, and that put us into the dry period. That's where the long-term drought started. A previous transition was 77, 78, and that we are in the, that was the wet period preceding to this dry period. Okay, so that's the role of the ocean. And then how does it look over the land? What here you are seeing is the standardized precipitation anomaly for the southwest. And if we just focus on our last period, last dry period that started in 1999 or 1998, you see, yes, that is a kind of dry period, but there are intermittent wet period, like whether when the precipitation anomalies exceeded that 0.5 standard deviation. And still, despite those intermittent wet period, we are seeing the long-term drought. So does the land process integrate that precipitation anomalies that is forced by the ocean, and then it produces you the long-term drought? So what is my talk is mainly talking about how can land process integrate these anomalies, and what are the implications, what are on the stake here. So this is one plot you can think about. What I'm showing here is the Illinois soil moisture observation for 1988 drought, and you see the soil moisture anomaly in color, and then the precipitation anomaly in the vertical bar. And you see the precipitation anomalies goes into the soil, and then it gets stored into the soil system, and then there is also suggestion that it appears to the root zone. It is important to recognize the difference between the root zone where most of the action takes place, or where if there is 2 weeks of the dry period, crop will start dying, versus the deep layer where that is a larger storage, but that is not always available. There needs to be atmospheric conditions that or the some other sort of anomaly propagation mechanism that can be tapped into the surface to be make available to the crop. Okay, that was a single event. If we construct statistics of the soil moisture observation, you see, the left-hand panel is a little easier. You see on the x-axis is the lag month, and on the y-axis is the anomaly correlation. You see there is anomaly correlation drop as expected. But what interestingly, we also see that anomaly correlation again picks up in that blue line, and it becomes statistically significant at 13 to 15 months. And that's where land can provide the source of predictability at the interannual time scale. Again, right-hand plot is a little complicated, but it's basically the same plot as shown in the left panel, but for all the season. And you see there is, and on the y-axis and x-axis are the different lags, and again, anomaly correlation drops and then again reappear, and you also see the slanted line that gives us some indication that it is seasonally tied. Okay, so the land atmosphere interaction, this can land atmosphere coupling feedback can by itself increase the memory in the mid-latitude region, and that can impact drought. So here is a result from an experiment that we run two land atmosphere couple and land atmosphere uncoupled experiment, and we are finding that it is increasing memory, particularly in the mid-latitude region. So what are the implications of those memories? Here I had a smart student, and he constructed a number of drought indices from SPI, or the soil moisture indices using the experiment data. And what we are finding that when land atmosphere is coupled, then you see that the blue curve that is always right side of the red curve that is uncoupled, and that means land atmosphere coupling feedback can make the drought longer as well as more severe. So how does it all look into the current generation of climate and earth system prediction system? I will say it looks okay. We compared the soil moisture predictability with the precipitation predictability, and we are finding that soil moisture has a 3 times higher predictability in terms of the spatial extent and also going through the time compared to the precipitation. Then our...
sorry to interrupt, but 1 more minute.
Okay, so have we reached the upper limit of the predictability? This is most complicated plot. On the x-axis, you see the lead month. On the y-axis, you see where we find the anomaly correlation is statistically significant, spatial extent. And in the brown line, you see the what is realized in the coupled system or earth system prediction system, and compared to some kind of observational estimate that is a black line. And what you find that, compared to the observation, only 1/3 of the total predictability, or even less than that, is being realized in the current earth system prediction system. So I'll go into the last slide. Hopefully, I convinced you the land process can contribute to the predictability at this time scale. Land atmosphere coupling feedback has been underrepresented in the climate model. This is the same plot, but for precipitation. And then finally, what one point I wanted to make here is, but it's exciting to see that many experiment is being taken place, or there is excitement to do more experiment, but we also need more measurement to constrain some of these long-term climate processes, particularly the deep layer soil moisture observation are not as extensive as we expected. So with that, I'll end my talk. Thank you.
Thank you, Sanjiv. We have time for a few questions. So the way I'd like to handle this is, if you in the online audience and you'd like to ask a question, please just type in the chat box that you have a question, and we'll call on you. And Matt, I'll sort of lean on you to help me identify people in the room in person that would like to ask questions. So please feel free to open into the chat box a question for any of our speakers, or Matt, just let me know if there's any questions from the audience.
I know there was one in the chat earlier, just before Adam. Who was that from? Bill, I think from Bill, if you scroll up or just unmute him.
Sorry. Bill Merrifield. Bill, do you want to unmute and go ahead and ask your question?
Sure. Yeah, the question was for Andy. So it's been shown for a couple of seasonal forecast systems out to 12 months that there is some skill for predicting snow water equivalent in the American West out to 12 months. And then so presumably sometime beyond, particularly for snow water equivalent in the spring. Just wondering if this is potentially useful for multi-year hydrological predictions, sort of besides the temperature and precipitation prediction information.
Yeah, I would say it is. I mean, if we go back to that concept of this predictable evolution of anomalies in certain components, such as snow or equivalent, and driving anomalies in other components, such as runoff and soil moisture, I do think if you could predict out to a year or more what the snow or equivalent anomaly would be, that would tell you a lot about what's coming in terms of runoff and soil moisture for up to another 6 to 8 months, depending where you are. So definitely, I would say that's a part of our strategy, perhaps.
Okay, thank you.
Any questions in the audience?
Yeah, Aaron Toller.
Hi, Erin Towler from NCAR. This question is for Adam. You had mentioned in your talk that the QBO is predictable in a lot of the models, but then the teleconnections are not. Do you think that it would be better to put our energy into trying to improve that in the model, or do you think statistical efforts to just relate them directly? Do you have any thoughts on path split on that?
Yeah, that's a good question. You certainly could use some kind of empirical correction to reinstate the teleconnection in your ensemble mean or something like that. And that's kind of the process that Bohr and Hamilton paper took. And the O'Reilly paper did that as well, actually. So that is an approach. So you could post-process it back in. But I think, we want all these things to be active and interacting in the model. So ideally, I think in parallel, maybe that's an approach until the problem's solved, but I think the weakness of the teleconnections in the forecasts is quite striking. It's appeared in many studies. So we're not really seeing the benefit yet in the forecast fields from the very high predictability of the QBO. So I think we need to work on that too. I wouldn't want to neglect that. I suppose I should add that I think that is probably yet another example of this so-called signal-to-noise paradox, where the signals are very weak in the extratropics. It could be down to the same root cause.
So let me take the chair's prerogative. And Yoshi, at the end of your talk, you were sort of making the case about initialization shock, and you were sort of arguing that the FOSSI has an initialization shock versus the ODA system, the anomaly initialization that you're using. But the thing I always worry about that is your anomalies that you're assimilating are inconsistent with your mean state. They could be very inconsistent, and that too could lead to a shock. So I was wondering if you had any thoughts on that.
Yeah, that was really great questions. And then particularly for the thermocline depths would be different between model and observation. So, but it's depends on how much strength you nudge to the ocean observation. If you strongly nudge to the observation, such kind of inconsistency getting pretty large. So what we did is we try weakly nudged to the observation. But this is kind of trade-off. If we weakly nudge to the observation, model drift getting lower, initialization shock is getting lower, but it's getting far from the real true state. So this kind of balance might be the challenging. So we need to do the couple parameter sensitivity study and then find a good kind of tuning. And then if works well, it go very well.
Okay. Noel, why don't you go ahead and unmute and ask your question?
What? Okay, that's fine. And then we have a question in the room after.
Sure. Noel, go ahead.
Adam, I was just wondering about so thanks, it was a very interesting talk. I was wondering about the Southern Hemisphere. So you talked a lot about the extratropics in the Northern Hemisphere. I guess the Southern Hemisphere has a similar QBO impact. And do we see a similar underrepresentation, a similar signal to noise issue there?
Yeah, that's a good question, Noel. There certainly is a teleconnection in the Southern Hemisphere because there are papers talking about how it modulates the depth of the ozone hole, for example, in certain epochs. That's very clear. I am not aware of a paper looking at the strength of the QBO teleconnection and arguing that it's too weak in the Southern Hemisphere, though. My feeling is that the teleconnection at the surface may be weaker anyway. But I'd have to check that. It's a good question. There's certainly a connection to the extratropical stratosphere in the Southern Hemisphere. And there are one or two papers arguing that our predictable signals, irrespective of the QBO now, but things like signals in the SAM, may be too weak in the Southern Hemisphere. But I'm not sure about the QBO teleconnection itself. It's a good question.
So there's a question from the audience.
Yes, this is Antonietta Capotondi. So my question actually is for Sanjiv and Yoshi and also to Andy a little bit. So both Yoshi and Sanjiv, you showed how precipitation and then water storage and soil moistures are constrained, are related, are forced by the tropical Pacific. So you showed the importance of the tropical Pacific for these quantities. So that calls into play ENSO, but also it's decadal modulation, especially if you go to the multi-year. So how important would be to, for predicting the quantities that you're interested in, to predict tropical Pacific decadal variability? Can we do that?
Yeah, so for my case, tropical Pacific would be the decadal component is very important. And then if we, particularly for Atlantic, because if we go to the tropical Pacific, ENSO signal getting more dominated, and ENSO time scale is much more shorter compared to focusing on low frequency component. So ENSO looks like acting like a noise. But as a tropical component is the main driver for atmospheric circulation. So I think tropical climate predictability, if we can enhance decadal predictability in the tropics, that will be pretty great benefit. Yes, thanks, Antonietta.
Yeah, I'll agree what Yoshi said. Like, yeah, it's very important for us. We take the tropical forcing for the land surface component. We take the whatever comes from the ocean as forcing. So if there are more predictable signal there, it will help us to better predict.
Anything to add, Andy?
Yeah, I would just say you have to think of these frequencies as kind of layering on top of each other. And if we're talking about year 2 predictability, certainly I wouldn't say ENSO is kind of a noisy part of the signal. It's a big part of the signal, but it also sits on top of the decadal variability that's lower frequency. So in places where you have a lot of land memory, you can see the decadal signal setting the stage for the impact of the shorter range signals from ENSO variability. And so that, I think, could be very beneficial.
Okay, we have a question in the room from Jerry Meal.
I'm not hearing anything.
Okay, how about now?
Yeah, there we go.
Okay, so I can recap for the rest of the room now that I've asked my whole question. What I was talking about was, we were talking yesterday about interaction of modes of variability in the QBO and MGO interaction that, Adam, you were talking about. But I was wondering if, the direction of the interaction. So you were talking about strong convection, tropical convection could, you have more upward propagating gravity waves, and that could affect the QBO, and maybe the QBO itself could affect the tropical convection. But is there, when you're talking about the interaction, has there been any work about the direction of the interaction, about one driving the other, or vice versa?
I mean, the direction is thought to be downwards in most of the papers, right? So people talk about imposing the QBO in experiments and trying to see a response in the MJO. There must be some upward interaction because the MJO is closely related to Kelvin waves, and those are very important in driving the westerly phase of the QBO. So there must be some interaction. But I guess the assumption is that the very long time scale and the great persistence of the QBO means that the perturbation, for example, whether you have an easterly or westerly QBO cannot be down to the time scale of the MJO. It is set on much longer time scales because it's integrating up forcing from all these transient gravity waves. So my feeling is that the way it's presented in the literature is probably about right, that if anything, it's a downward influence. And I think I've seen one or two examples where people have now tried to use kind of very high resolution, convection resolving models, and they show hints of the observed relationship. Yeah, so it's possible that there's an upward, there must be some upward influence, but I think that just the time scale of the MJO is so short compared to the very low frequency QBO that if anything, the sensible idea would be for a downward influence. So that's my feeling.
Okay, thanks.
So I think online, Carlos, you had your hand raised. Is that true? Go ahead, Carlos.
Hi, yes. I have a question. We have been talking about the long-term memory, how important is getting the right phases of this. What about focusing the attention of getting the short-term memory right? That can be made more beneficial. I'm thinking about like differential equations, how important is getting the right time steps or making the right as prediction of the next following steps. This is an open question for everyone in the audience.
Any of our speakers like to take Carlos's question?
Well, I could just say that I do think that makes sense, that we should be looking at that time scale as well, since that will, I think about hydrologic systems responding to this high frequency weather impacts, and then trying to basically filter that into a longer term, lower frequency signal. I do think one thing in our coupled Earth system model development, at least from what I see at NCAR, we pay very little attention to these kind of questions, like whether the persistence in the soil systems is correct or not. And that could have a huge impact on whether or not we get the right kind of decadal predictability in the models. So, hopefully we'll start to look at that more, not only at these longer timescales, but even down to the very process relevant, very short timescale reactions.
Nice, thank you. So Jenny is giving us the hook on this discussion session. So we have time for one more question from the audience.
Yeah, which I'm gonna steal.
Okay, and then but we also Jenny wants to do a virtual group photo also. So everybody who's online, please stay online for an additional minute or two while we do that online group photo. So Matt, go ahead for the question
just
from the audience.
a real quick question for Adam. So we've had in the last 5 or 6 years 2 breakdowns of the 2-year predictability of the QBO. So how confident are we really that we weren't just in a period of unusually regular QBO behavior, and maybe that's not the norm, or at least may not be the norm for the next couple decades?
Yeah, it's possible, Matt. I mean, I guess we had 60 years of OBS pretty much before we saw this. So, and now we've had 2 in the last few years. I don't think anybody expected either of those. I guess I don't know the answer to your question, but just a couple of extra bits and pieces. There are papers showing, certainly in a number of models, that in the future, as climate change progresses, that the QBO weakens in the lower stratosphere, and that may be partly driven by increased upwelling, which is pushing it back up and weakening the oscillation, but that perhaps could start to lead to an increase in disruptions, but we really don't know. We've searched through simulations in different models to try and find similar events, and there are occasional ones, more so in some models than others. And another point to make is that the dynamics of those events, we do understand to some degree. They are caused by extratropical Rossby waves propagating right into the deep tropics in the equator. And of course, the Rossby waves can only get in when the QBO is westerly. They can't propagate in through the easterlies when the QBO is easterly. So we know that disruptions only occur during westerly phases. So I can't answer your question, but I think those bits and pieces point to a possible increase in disruptions, a systematic increase in the future due to climate change. And it's always the westerly phase, I think, that will be affected. So, for example, if we had more wave activity in the future in the extratropics, that might be a possible reason that things could systematically change. And as you say, there could be internal variability, it could just be a fluke and might happen from time to time otherwise. Yeah.